Okay, so good afternoon, everyone. So thank you for joining the colloquium today, and it's a pleasure to introduce our distinguished speaker, Professor Swagato Banerjee, who is a professor in the Department of Physics at University of Louisville, USA. So Professor Banerjee is a leading researcher in the field of particle physics with particular expertise in the search for dark matter, lepton flavor violation, and other signatures of new physics involving tau leptons. He is currently working on the Belle II experiment at Super KKB Collider in Japan. He also worked in Atlas experiment, BaBar and L3 experiments. So he is currently serving as the convener of Belle II physics modeling and generator group, and he is also a member of Belle II Publication Council. In addition, Professor Banerjee is one of the convener of the heavy flavor averaging group and a member of PDG. So today, Professor Banerjee will be discussing lepton flavor violation, a cutting-edge topic in the search for new physics. The tau lepton, being the heaviest of the charged leptons, offers a rich avenue for investigating this lepton flavor violation search. So please join us in welcoming Professor Banerjee to the stage to share his expertise and insight on this exciting topic. Thank you.
About flavor violation, so I should begin by telling you what is flavor. Flavor is another name for the generations. As you know, we have the three generations of matter, and these three generations are instead of sometimes generation also called flavor. And these are the quarks and the leptons that are the three generations we are talking about. Very interestingly, we have already seen in the quark part there is a mixing happening, and this has already been very well established, and we have a theory called the Kobayashi-Masukawa mixing that describes this. In the lepton sector for the neutral ones, we also have mixing, which has already been observed in all different varieties. The part that has never been seen is the charged mixing between the charged sector, and that can give rise to the lepton number violation or lepton flavor violation, and that is the topic of discussion today. So first let me give a very general introduction, which I am sure all of you are very familiar with, about the symmetries of the particles in the standard model. So we have this local symmetry that is described by this SU3 cross SU2 cross U1, and that describes most of the local interactions. And in addition to that, we also have some global symmetries. These global symmetries are coming from in the baryon sector, or in the Le, which is the electron lepton number, muon lepton number, and the tau lepton number. And this symmetry can be written another way in this format, in the B plus L, B minus L, mu minus tau, and mu plus tau minus 2e. This is just writing the same symmetry in a different way. In the B plus L, we don't expect to see any observable effect. The B minus L is typically considered to be conserved. That is described by this symmetry, and this remaining symmetry is what is called the lepton flavor conservation. So this is the symmetry which mixes the electron and the muon numbers and can be written very conveniently in this way. And by lepton flavor violation, we mean non-zero values of the eigenvectors of this symmetry. And this is very nice because it gives us a way to classify all the lepton flavor violating processes, and that is given, for example, in this two-dimensional plane, where on one side we can have the mu minus tau, and the other side we have mu plus tau minus electron, and then all the points which are not at the center consist of different possible examples of the lepton flavor violating process. and they have been all studied to a certain extent or searched for, and we have so far no evidence of seeing any of them. But essentially any point on this plane outside the origin gives us a way to search for the violation of Lepton flavor violation. And also we can have a baryon number violation or lepton number violation, essentially the same way by looking at points away from the origin on this, but depends upon how we choose our process. Sometimes we can have a single baryon coming up, or we can have, for example, a case where the tau goes to an E plus and the lepton number itself is violated. So all these different examples of baryon number and lepton number violation are also included in this general way of categorizing all the lepton flavor violating processes. Now in the standard model, because we have the neutrals mixing in the neutral sector, that of course can induce also a mixing in the charge sector. For example, we can have neutrino tau changing into a muon tau, and that will of course give a charge lepton flavor violation. However, if you look at this diagram, it has the MW in the denominator and the neutrino mixing in the numerator, and putting in the numbers, we find this is of the order of 10 to the power minus 54 or something, which is very small, and it can never be seen, realistically speaking. So on the other hand, we can say that if we do observe a lepton flavor violating signal, it does not come from any standard model process. It is truly an evidence of new physics that we are looking for. And the sensitivity of this new experimental numbers are of the order of 10 to the power minus 8 to 10 to the power minus 10, which is the region where we are able to search and makes this search for new physics a very interesting one. I will briefly stop upon this example of tau going to 3 muons, which is described by a diagram like this. And there was a very interesting paper in 1999 that said that if we calculate this in the standard model contribution, it should be about 10 to the power minus 14. Of course, 10 to the power minus 14 is a very small number, but still it gave hope that if we do see this number at the 10 to the power minus 14 level, then we are actually not sensitive to new physics. And there have been several discussions ongoing about it since 99, and I particularly took upon myself to talk to several theorists from different collaborations. And finally, I found these two collaborators who were interested in really revisiting the calculation done in 1999 paper, and they found that there was actually a mistake in that calculation. Actual numbers for the 3 muons is really 10 to the power minus 54, which is same as tau to mu gamma. So we can lay to rest that if we do see any of these, then this is definitely not coming from any standard model related contribution. Yeah, I think they forgot a log or something, and instead of calculating the log as a fraction, they did a subtraction and found it to be cancelling, which actually does not happen. So some cancellation that the authors assumed would be happening in the calculation did not turn out to be actually cancelling. And in this, there are these new set of papers which independently cross-check this calculation and find it is really 10 to the power minus 50s level, and therefore there is no standard model prediction that is large enough. Yeah, so it was expected to be small, but some people were surprised at looking at this 10 to the power minus 14 number, and then they said that, okay, maybe if we make enough taus, we will see it. But no, there is really no hope for that. Okay, so these are the different ways we can actually see the lepton flavor violation in terms of new physics process. Some of these are tree-level process, some are loop-induced process, and they have different levels of sensitivity, which actually are just very close to our experimental limits, which makes them quite interesting. In particular, I have a set of old papers listed, but things haven't changed much. In most of the models, we expect the prediction to be lying between this 10 to the power minus 8, 10 to the power minus 10 level. And our experimental reach is now starting to go at that level. So we are hopeful that in some of these new physics processes might actually show up in our experiment. And okay, so I already said that there are many examples of lepton flavor violating process, basically any point on the two-dimensional grid away. In particular, we are very fond of looking at tau to E gamma, tau to 3 leptons, but these are not the only ones. The ones that contain some sort of a quark in the meson in the final state are very interesting because they get an enhancement due to the color factor, and that makes in some of these there is a prediction that the mu eta would be enhanced with respect to mu gamma by a factor of 8. Eta is just a very specific example I have taken of this paper, but there are other predictions also from different mesons like rho, pi. Several of them are expected to be enhanced with respect to mu gamma because of these color factors, and that makes search for all of them an exciting experimental activity. So in particular, we search for tau going to a lepton and a photon, or a pseudoscalar meson, or 3 leptons, and also lepton hadron final states. Basically as many detectable final states we can think of. Now there is another interesting point that says that the lepton flavor violating numbers in the limits that we have in the muon sector is of the order of 10 to the power minus 13, and the numbers in the currently available numbers in the tau sector of the order of 10 to the power minus 8. So if you are already ruling out the muon at 10 to the power minus 13 level, does it still make any sense to search for lepton flavor violation in the tau sector where the limits are 5 times higher? The answer is yes, because of the model dependence. Of course, we are all talking about different kinds of new physics phenomena that is coming up in through different new particles that we have not seen. But in general, because of this model dependence, we can expect that such a difference of the order of 10 to the power minus 4 or 10 to the minus 5 can easily show up. Not always, no. So here is a specific example where we are looking at, for example, I think this is an exchange where we have written the neutrino in this powers of this, and the Yukawa couplings are described like this. And then we can see in the terms of this parameter space, in some regions the taus are dominated, in some other regions muons are dominated. So because of this model dependence, in certain region of phase space, especially that is related to mass dependent couplings, the taus are still supposed to be smaller than at the 10 to the power minus 18 level, while at the same time muons can still be of the order of 10 to the power minus 13. So this is a particular example of a doubly charged scalar exchange, but there are several other parameter space that are also present. So the important point is that lepton flavor violation can really come up in many different ways, and to be experimentally exhaustive, we should search for them all. So this is a very brief overview of the different lepton flavor violating process, charged lepton flavor violating process that we look for in the tau sector. We can have direct decays of the taus into the final set that I just now listed, some even containing baryon, a lambda for example. Also we can have lepton flavor violation with the taus in the final state, namely those coming from B decays or Z decays or even Higgs decays that are not decays of the tau, but decays of heavier particles containing tau in the final state. And many of these are also having lepton-Floer violating signatures that are forming kind of an exhaustive list of different sets of reactions we can look for. And because of this large variety of final states in which, or interactions which we can study, we are really sensitive to LL prime is, for example, the LL prime is L plus and L minus. So D0 can go, so there are currently limits on E mu, D0 to E mu, not in the tau yet, but similarly you can have a D0 to pi 0 E plus mu minus. So we can have it in the D decays, in the B decays, and also in upsilon decays. The predictions of these are of the order of 10 to the power minus 6 in terms of the lepton-Floer violating limits, which I will describe towards the end. No, they don't have any. Massive neutrino would right. The standard model backgrounds are not overwhelming compared to the standard to the lepton-Floer violating signatures that we can have from different new physics. I will have some of these numbers later so we can see them. Okay, so we basically can look for lepton-Floer violation in many experiments, in super KEGB, of course, in LHC, and also in the super tau charm factory that is proposed in the future at EIC, FCC, and these are the different timelines where these different experiments will come up. We did a study of these processes at the SNOMAS activity and try to make a comprehensive survey in that link that is shown there. So in terms of the particle, final states that we have searched for in BaBar and Belle II experiments, there are almost 50 tau decays. I could not list all of them in one page, but some of them are very interesting because there are newer results that have come up. For example, in the 3 muon final state, or in the lepton plus an invisible particle final states. And very recently also we have a new result from Belle on the baryon number violating lambda final states. And the searches are kind of similar. So I will start with a particular one, for example, this one, which was published by Belle II a couple of years earlier, just to give an idea of how the searches work. So what we have in the final state is a lepton and a particle that is invisible. So this tau is decaying into a lepton and an alpha, which is not seen in the detector. So the way we try to search is, we, for example, look into 3 final state decays on the other hemisphere. The other tau is decaying into 3. And we take this 3 pion and sort of invert it to get an estimate along where the tau could have gone. Of course, this side has a neutrino, but this side does not have a neutrino. So there is a little bit of ambiguity in terms of the actual direction in which tau could have gone. But so that is called a pseudo rest tau rest frame. And in that rest frame, we look at the momentum of the lepton that is being seen, and then we can see the signal would appear like this, and this is the standard model background. The signal will of course depend upon the mass of this particle. So this is the general way that we search, by looking for differences in the shape of this lepton in the tau pseudo final state. And the limits and the coupling has been set by the Belle experiment at 95% level are shown here. They are smaller than the previous limits that were available by almost which one? So this is the two-body decay of the lepton. So lepton, we are looking at the momentum of the lepton in this rest frame of the pseudo tau. So this is because this one has a specific mass. So we are looking for example, it could be 0, 0.5, 1. It has to be less than 1.7. But for different numbers of masses, we look for the spectrum for this lepton, and that has a characteristic difference compared to the dominant background where tau decays into an electron and 2 neutrino. So that is shown by this the standard model background, and the signal is appearing like these shapes in the same distribution. Then we can make a template fit and search for how much of this signal may be present in the data that we observe. And from that, we get this sort of upper limits on the coupling. And these couplings are, the previous limits were from Argus from 1995 with about half FM to 1 inverse of data. And this has been updated by the Bell experiment with 63 FM to 1 inverse of data. And we are able to make an improvement by a considerable factor. Sometimes it's of course mass dependent, but almost a order of magnitude lower limits are obtained by the Bell experiment compared to the previous numbers from Argus. Now, coming back to this list, you see the tau to 3 muons is actually very interesting because it can be searched by the widest number of experiments. So for the remaining few minutes, I'm going to focus on this tau to 3 muons and describe how so what we actually look is the branching fraction. So what could be the branching fraction of this normalized to that of the electron? So tau can decay into electron that has a branching fraction of 17.8%. With respect to that, how much do we expect the branching fraction of this spectrum? Yeah? Yes, so of course models are giving, but this is purely experimental number without any model dependence. Yeah. No, it doesn't. That is very interesting because the reason why it doesn't depend on the spin is because the taus, of course you can produce a tau left and a tau right, but you are producing an equal amount of tau left, tau right, whether it is plus or minus, in an unpolarized detector. Because our accelerator does not have any specific polarization to begin with, you produce tau left, tau right, you also produce tau right, tau L. Because they are produced in equal amounts, that spin dependent is washed away. But on the other hand, if you did have a beam polarized machine where one of the electron was say 80% polarized, then you would be able to see the difference between the spin states of this. Yes, EIC, one of the plans is to have a polarized beam for the electron. And also there is a plan to have a polarized beam at Super Belle II if it is approved in some time in the future. Okay, so as I said, I will then describe the general way how we obtain the sensitivity. So this is the number on which we try to quote our results, 90% confidence level upper limit on the branching fraction of the signal process. This can be defined like this. We have the number of signal events, the N90, that divided by the efficiency times the number of taus produced is the upper limit on the branching fraction. And this efficiency will have different contributions, but in general it is going to be a number of the order of 5 to 10% depending upon the final state we are looking at. So essentially all the how small we are able to make this depends upon the number of taus. More and more taus we can study and produce, the upper limit will be dictated by that. So that order in number of taus is now approaching 10 to the power 10, 10 to the power 11 in the different experiment, and because that goes into the denominator of that calculation, so we end up numbers that are producing upper limits of the order of 10 to the power minus 7, 10 to the power minus 8. So it just depends upon the normalization of how many taus we have produced and analyzed. Because there are 2 taus produced, any one of them can go into the signal. In LHC, we do produce more taus, 10 to the power minus say 15, which is 5 times more than any other experiment. But typically the efficiency, even starting at the trigger level, is much smaller. This kind of efficiency we can get an E plus Siemens collider. In efficiencies starting at the trigger level and reconstruction level is smaller by about a factor of 10 to the power minus 3, minus 4 compared to others. So in the end, we end up basically getting however much taus we produce, this 10 to the power 10 times efficiency factor, and that is what governs the sensitivity of the experimental numbers that we measure. So this is a plot that is showing the our quantity of interest, 90% upper limit on the branching fraction, and it shows how the limits have gone down over the last 50 years, and now we are at the 10 to the power minus 8, 10 to the power minus 7 level, and essentially this is because of how many taus we have produced. As the years have progressed, we have produced more and more taus, and this is falling kind of like a square root, maybe you can say, with respect to the year, but this hopefully will reach the level of 10 to the power minus 8, 10 to the minus 10 around say in the next decade or so, and that is what makes it very exciting, because this is the region where we expect all the different models to be predicting where the lepton flow violating sensitivity is. Most of the models are still there. Some models have been ruled out. In fact, some of the parameters of these supersymmetric models have been ruled out. But some parameter space still gives predictions of lepton flow violation of the order of 10 to the power minus 10, 8 level. And that is exactly. Okay, so let me then focus on the tau to 3 muon final state, which has been seen by the most experiments. In particular, we'll start with the B factories, the electron-positron annihilation. In electron-positron annihilation, because of the initial state being electrons, and we can measure the momentum very well, we get 2 constraints. One is the mass constraint, and other is the energy constraint, which are 2 independent numbers that we can plot on a mass versus energy plane. And then the signal is supposed to be in a small region, depending upon the experimental resolution, of course. But within the resolution, the signal is focused in a very small region, and everything else that we see on this plane is background. So it gives us a way to kind of narrow down the way of sensitivity and focus upon the signal in, say, for example, 2 sigma region around the 0 in the delta E, and m tau in this mass plane. Of course, we are helped by the fact that our experimental machinery is becoming better and better with momentum dependent particle identification, and we now have more machine learning techniques. So all these help us to improve the results even better. So here is the result that we have from BaBar with the 10 to the power 3.3 times 10 to the power minus 8 with 468 femtobarn inverse of data, and the result from Belle is 2.1 times 10 to the power minus 8 times with 782 femtobarn inverse of data. These results mostly came in the 2010s. They are old by almost 15 years, and but they are still one of the best limits that we are grappling with. And the goal is to meet and exceed these numbers with our Belle II and LHCb or LHC experiments, and that is where the phase we are in right now. So after 15 years of progress or no progress, we have now come down from 3 times 10 to the power minus 8 to 2 times 10 to the power minus 8 with a slight better sensitivity, and the efficiency has improved. And this is the signal region, this 2 sigma signal region, where we see one event in the data, which is completely consistent with the background prediction of 0.7. And this allows us to put a limit with Belle II 1.9 times 10 to the power minus 8, which is the most stringent limit that we have been able to put so far. Also, because of this final state is accessible in several experiments, there also has been a search about 10 years ago by LHCb, and this search was done with 3 femto-1 inverse of data at 7.8 TeV, and the result that they obtained is 4.6 times 10 to the power minus 8, which is kind of a similar order of magnitude, you will say 10 to the power minus 8 level. But I am told that the LHCb is now trying to use the full data set and improve upon this limit and come closer to other results from other experiments. In the long term, when we have upgraded in the future and LHCb collects about 300 femto-1 inverse of data, there they expect to be able to go down to 10 to the power minus 9, which will be really fantastic if we can reach that from different experiments. But that is the general statement that LHCb has made, that they will be able to go down to 10 to the power minus 9 level by the end of their experiment. Atlas numbers, CMS numbers. Atlas had a result from about 10 years ago, 2016, that is 3.7 times 10 to the power minus 7, which is actually an order of magnitude lower. But that used a very small femto-1, 20 femto-1 inverse of data at 8 TeV. They are also trying to use their new run 3 data, but the results have not yet been made public. CMS, on the other hand, did come up with a result that was released a few years ago, and they were able to reach 8 times 10 to the power minus 8, which is already approaching 10 to the power minus 8 level. And the expected numbers that we can see from the new search that was that came out last year is that they are able to improve from this 8 times 10 to the minus 8 to about 2.9 times 10 to the power minus 8. So this is the result that they obtained by including the data set at 13 TeV. And by 13 TeV and that was at 8, and now we have they have come down to 3 times 10 to the power minus 8, which is already very close to the result that we have from Belle II. Mostly vertexing. Yeah, so they have the 3 muons, and they are able to vertex it very well and differentiate that from backgrounds that do not have a 3-prong vertex. So that, and then the point is that they can produce a lot of taus from W. So this has a large normalization factor, and then background suppression is now they have able to come to this level. So actually from the heavy flavors, from the B decays, they get lot of taus, much more than we get in Belle II. But the efficiency is of course severely constrained, because if a tau is coming from heavy flavor decays, it has smaller momentum. So because of smaller momentum, they have to fight with their trigger thresholds to see these low momentum muons. But by vertexing even at the trigger level, they are able to move their sensitivity better. So I think I will have that number in the next few slides. So here is the numbers that I have quoted so far from LHCb, from BaBar, from CMS, from Belle, also from Belle II. And in the HFLAB, we very recently came out with a combined upper limit that includes precision from all these different experimental inputs. And the method that we did was, we started with these upper limits from different experiments and tried to find the central number. So essentially we expect a, so this is the upper limit. Upper limit is typically mu plus minus 1 point some number times sigma. It depends upon this Gaussian approximation, but approximately we can imagine that the upper limit is 90%, so it corresponds to 1.64 times the sigma. So from these upper limits we can try to obtain where is the central value. And also we were very much helped by the fact that all the different experiments did have the central value and that they provided as inputs. So from the different central values we obtained the from the experiment we obtained those red dots, and then using their published numbers and these inputs of the red dots we obtained the error bars. So these error bars are obtained with respect to the defining the upper limit at 90% confidence level. So now we are able to find this the so-called central number plus an error on all of these experimental inputs, and then we can combine them from our traditional way, the usual way we combine different numbers using the error as the 1 over error square as the weight, and then we obtain the combined number, which is 5.4 times something of the order of 10 to the power minus 9. And then we again use the Gaussian toy Monte Carlo method to obtain the upper limit, a combined upper limit that we are able to obtain at 1.6 10 to the power minus 8, which is slightly better than all other numbers. So this has the precision power from all the experiments combined, and this gives the most stringent upper limit on the 10 to the power minus 8 level on the 3 muon process. Because our experimental efficiency is better, then the number of taus produced directly goes into the background in the denominator. But as I said, in LHC, the normalization is not the dominant factor because they have to fight with the backgrounds. So there the efficiency, because that is much smaller, so it is lower. But eventually all these errors from CMS and all, they have the error bars that we can obtain from the experiments, like the way I described. So yes, so eventually we can combine them, but the E plus E minus being a cleaner machine offers the best sensitivity. Okay, but once we have done it for 3 muons, you will say, why not do it for all the 50 possible channels that we have done? So this was also done in the flavor, in the EastFlav report that came out earlier this month. We took all these numbers for all the 52 different decay modes that has been searched for and obtained combined upper limit for as many of them as possible. If sometimes it is only one input from the experimental side, there is no point in making a combination. But if there is more than one from the different experiment, we have tried to combine. And this 3 muon channel is the most interesting. It has the most number of inputs from all the different experiments, and we obtain these limits. Now there is a slight problem in this method, because we are depending upon the fluctuations of individual experiment. Sometimes it can happen that the combined upper limit is slightly worse than the best upper limit by giving from the different experiments. And this has been done for the 50 different cases, and for 4 of these branching modes that I am highlighted here, this situation happens, that the star that is showing the combination is actually slightly, it's very difficult to see because the differences are quite small, but the best upper limit from the experiments is actually better than the combination. Because the combination is trying to have the best precision, best smallest error, but sometimes due to fluctuations, the central value itself can go lower than the fluctuation. And this we have tried to analyze for all these different 4 channels, and really what we understood that this comes from one experiment having a downward fluctuation, the other experiment having a upward fluctuation, and that is what causes a central value to be slightly shifted. But of course our combined upper limits have the best precision in terms of the error, but sometimes the central value can move around within about 10%. Okay. So having told you how to obtain the best combined upper limits, let me come back to the question of what is the best precision we can obtain in the future. Start with the atlas. So atlas is saying that we can have 3 different scenarios. One, we have high background, other we have medium background, and other we have lowest background. And in these 3 different scenarios, the normalization times efficiency is so-called optimized to have the same number. But then the background expectation is very different, and from there we can obtain the upper limits corresponding to 3 ortho 1 inverse of data in the future. So if we make a combined upper result of the 3 ortho 1 inverse, they are obtaining upper limits of the order of 10 to the power minus 9. Same story from also CMS. Their best limit is 3.7 times 10 to the power minus 9. This is what they can expect to reach in about 3 ortho 1 inverse of data that they expect to take over the next decade. And of course, this includes the fact that we have a lot of taus coming from Ds and B decays, which drive the normalization higher because that produces more taus. But in the end, the background optimization is what plays the sensitivity. We have also done this exercise for Belle II, assuming that we are going to see 5 ortho 1 inverse of data sometime in the near future. These green numbers are obtained, which is of the order of 10 to the power minus 8 and 9. And if we go all the way to projections of 50 onto 1 inverse of data, the projections are well below 10 to the power minus 9 level. And that would be really exciting because this is where most of the sensitivities are from the new physics models. For most of these channels, the sensitivity just goes as with the luminosity. But in certain cases, we have, for example, the particularly difficult channel of tau to mu gamma and tau to E gamma. There is some residual background. And if there is a residual background, the improvement doesn't quite scale. It doesn't scale as 1 over L. It scales as 1 over square root of L. And that is why you see the first 2 numbers are higher, and everywhere else, because the background levels are much smaller, we expect to be able to go down to 10 to the power minus 10 level with the full data set. We hope eventually they will give similar results, but so far only tau to 3 muon results have been published. Tau to 3 muons are expected to give similar results, but those because of the electrons radiate more, so those corrections are now being studied. But we did obtain similar results in the Belle and BaBar for both these channels. So after the analysis of Belle and BaBar was done, electron and muon channels were at the same standing. But in Belle II, we have still not completed the electron analysis. We did it for all of them. No, for tau to E, there is only BaBar and Belle. Yeah. Right. Right. Actually, in LHCb, it is difficult, from the LHC experiments, it is difficult to see electrons because of the radiation. Also, the same problem happens in Belle II. The photons from the Bremsstrahlung lung confuse us with the delta E measurement. But in E plus E minus, we are able to calibrate it in different ways to be able to overcome that. In the LHCb experiments, they have not so far been able to search for tau to 3 electrons yet. Yes, so all those combinations gave similar kind of results in BaBar and Belle experiments, but in Belle II this has not yet been shown yet. But we expect to be able to do that for all the different channels in Belle II. But we don't even expect to be able to do all of them in LHCb. Okay, and next, moving on to the future, how much can we expect from the STFC experiment? Well, their numbers are with 10 autobahn inverse of data. They will also be able to reach 10 to the power minus 9 level for the mu gamma, and for the 3 muons, 1.4 times 10 to the power minus 9, which is again very hopeful. Hopefully, in about a decade of data, they can reach this kind of precision. EIC is also very exciting, and in particular, yes, they also have polarized beam. So in EIC, we don't expect to see mu transitions, but we expect to see the electron transitions. So because it is electron proton collisions. So from there, if we produce a tau, then they can compare the results that they get from EIC and the previous generation experiments, and compare with respect to the results that BaBar obtained for tau to E gamma, which continues to be one of the best limits, 3.3 10 to the minus 8. And then they put limits on the scale, and the scale limits are put depending upon which operator you are looking at, and the predictions are that they are able to move down from the previous generation experiment by an order of magnitude, with about, I think, 100 femto-1 inverse of data. That is the analysis that they have done. Finally, we also have a lot of hope from FCC. The numbers are still very preliminary, but from the mu gamma side, their expectation is 10 to the power minus 9, and from the 3 muon side, they do able to go down to 10 to the power minus 10 level, which is very exciting, although will take few more decades to come. Okay, so this is the summary of all the results that I have shown here, coming from LHC, LHCb, Belle, STFC, and EIC, all in the same plot. That the 3 muon line is here, which is the most populated line, and the predictions are of between 10 to the power minus 9 and 10 to the minus 10 in the far future. Next, I'm going to very briefly show the results of lepton violation with taus in the final state that can come from this kind of processes, from the B decays or from 2B upsilon decays, and also from chi B and so on. So these are the different kind of processes which predict lepton violation, and the summary of these results are shown here. So we have D0 to electron. We also can have baryon number violation, D0 to proton, 3 body final state from D plus, from B0 decays, from B sub S decays, and the upsilon states decays. All the limits are of the order of 10 to the power minus 5 to 10 to the minus 6, which are very challenging. The experiment, the theoretical predictions in the different models. Most of them are background free, but some of them have a certain number of background. A particularly difficult one is the B sub S to mu tau, B sub S to E tau. These numbers are 10 to the power minus 4, which are kind of high compared to 10 to the power minus 7 numbers that you see elsewhere. But these channels are very difficult to have a good efficiency for reconstruction because of the number of missing constraints that we have. They have searched for pi 0 to E mu decays, and those numbers are also available of the order of 10 to the power minus 4 or 5, if I remember correctly. But that has also been searched for, yes. Pi 0 eta, that has already been done. Okay, next is a very interesting part of lepton violating search that we can do from the Higgs. So we can look into Higgs to 2 leptons, an electron and a mu, and then we have the Yukawa coupling that we can use to compare the results from the Higgs decays and from the low energy tau data that we obtain, and then we can make these constraints on the 2 Yukawa couplings versus the mu tau or the electron tau, searches. And that is very exciting because LHCb is able to put limits that are in some cases better than the low energy tau data. You can see that the experimental limit from Higgs to mu tau is already lower than the mu gamma predictions, and in this case also for the electron case, these are the numbers from CMS that were produced very recently. There is also similar results from Atlas, and Atlas sees a very interesting tension in this branching fraction of mu tau, Higgs to mu tau versus Higgs to e tau. There the difference between the best fit value and the standard model is about 2.1 sigma. Well, 2.1 sigma is not 5 sigma, but it is still exciting to see that the error bars are the central value for the standard model is outside the error bar of the 2 sigma window, and that gives us some interesting hope to keep on searching on these channels. These are the numbers that Atlas put out in the Higgs to e tau and the Higgs to mu tau sector, and then there is also a prediction that they have how well will they be able to do with 3000 femto-1 inverse of data in the high luminosity phase, and there the prediction is that they can go down to about 0.1%, mostly because they can't drag the systematic any smaller. So statistical error will of course fall very rapidly, and it has already so this study is no longer statistically limited. So we do not expect the improvement to directly go as luminosity, but they are basically stuck with the errors that come from the hadronic differentiation between a quark jet and a tau jet, or a gluon jet, for example. So they are balancing the systematic errors on the jet identification for the hadronic taus, and that is what is driving this sensitivity to about 0.1%. But even with 0.1%, as I showed in the previous page, they are competing with respect to the low energy data that we have from tau to mu gamma, tau to e gamma. So obtaining the systematics limited study from LHCb is already a very important contribution in this search. Okay, now coming back to our two-dimensional search grid of the different dimensional operators that we can have to give the limits on the Lepton flow violation, we can then take all these experimental numbers and start putting bounds on the Wilson coefficients. And this is an exercise that has been started with all the different 888 of LFV operators. In particular, they looked into the axial current, the dipole, the Yukawa, and the 4 fermion contributions from all these different final states. And some of them are actually also aided by the fact that EIC is able to constrain the tau to electron transition, and that also gives some constraint on the Wilson coefficients. So this was shown last year at the tau conference, that all these different branching fractions are able to constrain the different Wilson coefficients for the quark transitions. No, so this is looking at the branching fraction. So in the scale where the branching fraction of, for example, Higgs going to tau tau is 6.3%, in that scale we are looking at the normalized to all the Higgs decays. No. So in the framework where the branching fraction for Higgs going to tau tau is 6.3%, in that normalization this is 0.1%. So the coupling that I showed here, the future limit will stay at the 10 to the power minus 3 level, because that is 0.1 times percent. So this is the observed limit. Now it is 2 times 10 to the power minus 3. It may come down to 1.5 10 to the minus 3. So essentially these limits of LHCb or the CMS Atlas will not change much over the next decade. But the important point is that this is already better than these ones. These ones are going to go down statistically with as the luminosity increases, they will drop by a factor of 100 perhaps. That is a hope. And in the FCC also and the STFC, they will all drive down this 10 to the tau to mu gamma and tau to E gamma. So these are not systematically limited. So these are a floating target that will try to approach, but in this particular set of operators, as I will be mentioning soon, the Atlas and LHC CMS limits are the dominant one that constrain those Wilson couplings. Yes, so I will make a comparison of the different processes. So yeah, so here what I am showing here are all these dipole and the axial and the left-handed, right-handed operators. These are all constraining different Wilson coefficients, which are then plotted here. And then in terms of the okay, so this diagram is kind of complicated. On one case, we have the limits and the bounds themselves, and on this side, it is the inverse of the divided by lambda to the power 4, of course, of the new physics scale that we can search for. So here, the smaller the scale, the more powerful it is. And then we try to ask, among the contributions from the color scheme is green is EIC, and the LHC is blue, and the tau data is shown in red, which one is giving the smallest? So here you can see that in this kind of couplings that describe this operators, the smallest comes from tau to E gamma. But in the couplings where it is dominated through the Yukawa, there the blue line gives the best limit. So depending upon and the same picture is also true as you extrapolate to high luminosity. So the point is that for most of the processes, tau data with tau decays is quite constraining, but for some of the processes which are related to the Yukawa couplings in particular, there the Higgs decays are more constraining. And this is generally true for this page is showing for the tau to electron transitions, and similar diagram is also available for tau to muon transitions, and all the different coefficients are listed here. And then we try to see, based on our improvement from the luminosity side that we can get from going to all the way to 50 Autobahn inverse of data, how much smaller will the Wilson coefficients be bounded. And there we see the most of the dominant results in the tau to muon sector come from the Belle II experiment, except for the case where the Yukawa couplings are involved, and there the CMS and LHC results are going to be interesting, at least while they continue to remain at the 0.1% level. Also, I skipped a page. Let me show that. This is another way to look into leptoquark couplings. So leptoquark couplings in the green is shown the limits from EIC. In blue, you can see the limits from CMS because it's a two-dimensional plane. And the tau decays, the ones that we get from the Belle II experiment, are shown by this band here. So it's quite interesting to see the bands and the radius or the diameter of the blue that is coming from LHC are actually in competition with each other. They are overlapping over a very tiny region where in one dimension Belle II is interesting, in another dimension LHC is interesting. This is actually done with 100 femtobarn inverse of data at EIC, but they are hoping to be able to improve it further. So this is the dotted line that they can predict from 100 femtobarn inverse, and maybe they will also take more data and improve their analysis techniques, because now it is very preliminary. So in the future, it seems that they will also be very competitive and interesting. Okay, this brings me to my summary page, which I am not going to list all the different numbers, but they are here for reference. Tau to mu, 3 muons are most exciting because it is projected by a large variety of experiments and will come down to 10 to the power minus 9, 10 level. And as we mentioned, that there is this very exciting possibility to have polarized beams at EIC and also at perhaps Belle. These polarized beams helps in a way that it can reduce the backgrounds drastically. The signal, if it is coming through phase base, would not be changed much because of the beam polarization. But if we use the beam polarization, we are able to constrain the standard model backgrounds even better. So with polarized beams, the standard model background comes down, even though the signal doesn't. But because eventually we are related fighting with signal to background ratio, we are able to make better limits with the projected sensitivity with polarized beams. And also the luminosity is one of the most important factors that will drive this in the future. With the polarization, so we had a white paper a couple of years ago, study for the Belle II, and the improvement can be about 15 to 20%, roughly. Yeah, I have not seen this number with and without polarization for EIC, but for Belle II, we are able to hope between, let's say, roughly 15% improvement can happen. Okay, and that's all from my side. Sure. Yeah. The improvement is actually not in that channel. This improvement was done for the mu gamma search, but whether we are able to improve, how much we can make an improvement on with polarization on this, there is no current result on that. But you can already see that you are able to constrain this. So this is a dominant standard model. So if you are able to cut this down by say 20%, you are already going to get an improvement in the search for that. So yeah, this is one of the study that is ongoing, and preliminary results are like similar 15 to 20%, but there is no public result yet that we can show. Yes, once you have a polarized beam, you can actually, the point is that here I am showing two masses. The red one is 1.4 GeV for the alpha, and this one is for 0 GeV. For the 0 GeV case, if the mass of the alpha is very small, then it turns out there is no improvement that you can way to separate between the spin 0 and spin 1. But when the mass comes closer to the tau in this region, there you can differentiate between the spin and a vector state. So in the once the mass of the alpha becomes more than 1 GeV, then yes, you can try to separate that based on a spin analysis. And there, of course, if you have a polarized beam, you will be able to make a good discrimination. But in this region, when in the yellow where it is 0 or less than 1 GeV, then the separation is not so practical.